Hello everyone, I'm John Alexander representing SPM Labs LLC, introducing the Dynamic Cantilever Calibrator, or DCC for short. This version of the DCC is designed primarily for use with the multimode and dimension microscopes. Here is the DCC software directory. I have highlighted the live acquisition program SPM Labs _DCC.exe. Note there's also an offline version for analyzing saved data, the SPM Labs DCC offline.exe. Here is the DCC user interface, the experimental settings on the left, the active data display in the center region, and the analysis controls on the right. I won't go into great details on the controls in this video, just a quick overview of the main controls and features. On the left, you select the cantilever from the included library, or edit the library and add your own cantilevers. You also select the medium the cantilever is in, whether it's air or water or something else. You can also edit this as well. And of course, we also need the absolute temperature of the cantilever to do these calculations. In the lower left, we have the acquisition controls. You can select the deflection channel or lateral force channel as inputs. You can also select the sample rate up to 16 megahertz. And you can also select the input voltage range of the signal. In the center, we have the average power spectral plot. In the upper right, we have a tiny plot of the raw time domain data. At the top, we also have controls to start and stop the averaging and the legend for the spectral plot. In the upper right, we have a line for notes to be saved with the data. Below this is the analysis section where, from the Lorentzian fit to the spectral data, we find the resonance frequency and Q factor of the cantilever. Using the Sater method, we calculate the spring constant, and then from the spring constant and the power spectral data, we're also able to calculate the inverse optical sensitivity in meters per volt. Below this, we also give you the noise floor in meters per square root hertz. In the bottom right, we have the export menu. You can select to save your data in our binary format, or as an Excel file, or CSV, or others. Let's switch to the live software. Here we're going to reset the number of averages to 500. This will take about 1 minute at 8 megahertz sampling rate. You can see we can already see the second and first eigenmodes. Zoom in on the first. Zoom in a little more. You can see it's smoothing out already. And we're already halfway through the 500. It's pretty smooth. Yeah, this is an FESP probe, and the medium is air. And there we go. Okay, the red line is the fit to the data. We see that's 84 kilohertz. The Q factor is around 210. The spring constant's 2.9 newtons per meter, and the IOS is 94 nanometers per volt. And we also see that the noise floor is around 300 femtometers per square root hertz. Besides calibrating the spring constant, the DCC is useful for other applications, including finding the cantilever resonance in water. These are spectra of the same probe, on the left in air and on the right in water. You can see that the Q factor is much lower on the right, and the amplitude has also dropped significantly. The resonance frequency on the right is around 4.5 kilohertz. And if you look on the bottom, we have the tapping mode frequency sweep. And the first peak on the left of that spectrum is at 4.5 kilohertz. All those other larger peaks off to the right are probably associated with the liquid cell and not with the cantilever itself. Another application is in MultiFrequency Techniques that use the eigenmodes of the cantilever to mechanically amplify the signal. Here we're showing that the The DCC can easily find the eigenmodes of the cantilever. In this case, it's all the way out to the 7th eigenmode at beyond 1.2 megahertz. Another application. Some methods, such as piezo force microscopy, can use the cantilever's contact resonance modes to enhance the small signals. These are much smaller than the free resonance amplitudes, but are usually easy to detect with the DCC. The top two plots show the free resonance of the cantilever at around 25.7 kilohertz. The bottom two plots show that the contact resonance is shifted up to 140 kilohertz. The DCC is available from SPM Labs, LLC. Thank you for watching.